Welcome to lecture number 36 of the Statistical Thermodynamics course. As you can see that we have now done quite a bit of work now, for the row vibrational case to identify individual row vibronic transitions occurring within a visible or the UV spectrum. The spectroscopists have developed a scheme similar to the row vibrational counterpart. So spectroscopist scheme, okay, for the row vibrational part of the spectrum, row vibronic part of the spectrum. So the notation will be, the notation invoked, notation will be something like this. It will be to designate rotational shift, okay, is I j double prime equal to p q r I equal to 1, 2, 3, so on and so forth. So B is equal to P for a line in P branch. Okay. B equal to Q for a line in the Q branch, which we already saw. And P is equal to R for a line in R branch. Okay. The numerical subscript is less significant. It is sometimes used to identify closely spaced transitions, okay, various spin split levels within a multiplet. Okay, for electronic spectroscopy, however, we need additional. For electronic spectroscopy, we need additional nomenclature. Okay, additional nomenclature to designate the vibrational and the electronic shifts. Designate vibrational. This is only for the rotational part that we just did right now. Vibrational and rotational shifts. Okay. So the usual notation will be, notation is, try to do the notation part, it is A X double, something like that. Okay, so where only one arrow can be used, to the left for absorption or to the right for emission. Arrow, left arrow designates absorption, right arrow designates emission. Okay. Okay, so the lower vibrational level can be associated. So the lower vibrational level, okay, which is the double prime, it is associated, okay, with any electronic level, with any electronic state, which is given as X, A, B. Okay. In contrast, the lower, the upper vibrational level, this was for the lower, upper vibrational level, which is the prime, okay, should occur, must occur within higher electronic state. C. So as an example, a specific transition in the ultraviolet spectrum of hydroxyl radical, for example, which is very important in the case of combustion research, would be identified like this. So let's go to the next page, write for hydroxyl radical, what will happen. Okay, so as an example, specific transition okay, in UV spectrum for OH radical can be identified as Q19 A2 equal to 1 2 equal to 0. Okay, this indicates that J double prime equal to J prime equal to 9 in Q branch of OH as produced by the absorption of radiation. So it is the Q branch of OH, J double prime equal to J prime equal to 9. Okay. As produced by absorption radiation from double prime equal to 0 vibrational level in the ground electronic state to V the prime equal to 0 vibrational level in first excited, which is 2 sigma electronic state. Okay. So we have established in this particular chapter practical link between quantum mechanics and statistical thermodynamics through spectroscopy. So basically, if you recall that thermodynamic properties of atoms and molecules would be evaluated from their given energy levels and degeneracies. That's why we needed the quantum mechanics. So these microscopic parameters can be predicted and understood definitely using quantum mechanics. So, but however, quantum mechanics models are pretty complicated, okay? And so we need to resort to spectroscopic measurements, okay, for determination of various energy mode parameters, such as, omega E, for example, rotational constant B, and all these things. Okay, so in order to determine all these things, we needed spectroscopy. Okay, to fill in those gaps. Okay, so through spectroscopy, we can determine the energies and the degeneracies of the electronic states, and this allows us to now use these parameters in the statistical thermodynamics realm and to calculate the various thermodynamic properties, for example. Okay. So before we go let's take one example of molecular oxygen. This is we call the energy mode parameters. Parameters for the lowest electronic states of oxygen, O2. Okay, so this is essential because this is how these things are tabulated. So just to show that how things are tabulated so that we can find out all these degeneracies and other things. So then there is TE, then there is omega E, and then there's omega E XC. Remember, this comes from a complex model, then BE, and then you can find alpha E. I will not write all the terms, but I mean, definitely you can write them all. G, This, for example, 0. This is 1580.19. And it is 11.981. Then B is equal to 1.446. Then, of course, you have 1 delta G, which is 7918.1, 1483.5. This is 12.9. This is 1.4264. So similarly, you can write it for alpha E and D also. And 1 sigma G 13195.1, 1432.77. This is 14.0. This is 1.4004. And so on and so forth. So these are the different term symbols. You can write it also for alpha E, and you can also write it for D. These are all in centimeter inverse. Okay, they're all in centimeter inverse. Okay. It is in the wave number space. It's also centimeter inverse. It's also centimeter inverse. Okay, so you can write it like that. So so this is how you actually calculate the different things. Okay, so if we can give you an example, say for example, we the observed, so this is also example from the book, example 7.3, the book. Say the observed frequency, say the observed, and we will have tutorials on this, spectral frequencies, centimeter inverse, corresponding to some significant vibronic transitions, within A1 X1 electronic system of N. Okay, so let's look at this table. So the vibronic, it is given like this: vibronic transition, then there is frequency. Okay, so A1 pi equal to 0 to X1 equal to 0. A1 1 sigma plus equal to 0. Then of course A1 pi equal to 2. Then it is X1 sigma plus equal to 0. This is 39699.1. Is 40786.8, 41858.9. Okay. So using this data, calculate. The question is calculate, okay, omega E and omega E XC for A1 pi electronic state of PN. That's a requirement. Okay, so the band origin. So in order to the solution part is like this. So the band origin for any vibronic transition okay, is given as Just follow the steps. These are all we already have done. Okay. Now for this specific transitions indicated in the above table, so when you take the specific transitions, H prime equal to 0, double prime equal to 0. For this particular transition, T prime is 1/4 prime xc prime minus double prime minus 1/4 omega double prime x double prime. Okay, then of course you have b naught, b prime equal to 1, b double prime is equal to 0. Okay, this is equal to t b by 2 omega prime 9 by 4 prime x prime double prime 4th prime x prime equal to 2, double prime equal to 0, which is equal to now e by 2 by prime 25 by 4 prime e double prime 4 x. Okay, so if we subtract the first of this equation, which is this one, okay, from each of the remaining two equations, so you subtract this from this and this, so we get minus 0 is equal to omega e prime minus 2 omega e prime x prime. Okay. That is equal to 40786.8 minus 39699.1, which gives you 087.7. Okay. And then you do the same to as v double prime equal to 0 minus again v naught 0, v prime equal to 0, v double prime equal to 0. Subtract this, this will give you 2 omega e prime minus 6 prime x prime, which will give you 418.9 minus 39699.1, which is equal to 2159.8. Okay, now if you solve these two equations now simultaneously, simultaneous solution of these two equations will give you omega e prime is equal to 1133 centimeter inverse, omega e prime x prime equal to 7.80 centimeter inverse. Okay. So this is a standard solution that we did. Okay. Subtracting, just by subtracting, the method of subtraction to equations. So this will enable us to calculate, as you can see, given the spectroscopic table, the spectroscopic transitions, if somebody has measured this for you, you can find out these varieties of spectral parameters. Okay, so as you can see that we saw that we have covered a lot of materials in this particular part of this chapter. We know what are the different transitions, what are the different Ro-vibronic transitions, and stuff like that. So, so let us right now put the energy and the degeneracy for the energy modes of an atom or a diatomic molecule. Okay, so let us look at this table. So we can name this table as energy and degeneracy. Degeneracy for the energy modes, or the energy modes of an atom or diatomic molecules. Okay, so let us do this. The first one is the energy mode. Okay, then it is the energy, all are in centimeter inverse parameter, also in centimeter inverse, and then of course the degeneracy. Okay, the first one is the translation. Obviously, translation. Okay, so that is given as, you recall, 1 square plus n2 square plus n3 square. Where you have put some markers so that it's easier for us to write. And alpha TR was equal to, if you recall, H divided by 8 MC to the volume 2/3, and the degeneracy was quite a bit, 2 pi to M. This almost appears continuous. That's why spectroscopically this is not a very good thing. Translation on yeah, so that was the degeneracy for the translation. Okay, then comes rotation. The mode is rotation. It's J into J plus 1 to BE. BE, the parameter BE is H divided by 8 pi square C mu RE square, and the degeneracy was 2J plus 1. Then of course comes vibration. Vibration, okay, vibration is half E plus half omega E, and then omega E is given as 1/2 pi C root over K naught by mu, and the degeneracy was 1. Then you have electronic for atoms. So this is tabulated. T is tabulated. Okay. And the degeneracy is J, 2J plus 1. And for molecules, again, this is T is tabulated. This is, parameter phi 2s plus 1. Okay, so we have the translational energy, and we also have the no other energy mode is affected by the macroscopic properties, unlike translational. The internal energy modes, the degeneracy is like a probability distribution function for translational mode. For the internal modes, we recall the rotational constant for the rigid rotor and vibrational frequency omega E for the harmonic oscillator. Okay, similarly, spectroscopic measurements provide tabulations for the electronic energies of both atoms and molecules, which you see over here, atoms and molecules. Okay, for atoms, the required degeneracy is evaluated by summing over a multiplet caused by the different J values. For molecules, we typically sum over the multiplet caused by spin splitting and doubling. In other words, both atoms and molecules, the relative expressions are the effective degeneracies. So these are, as we know, the effective degeneracies. Correct. Okay, so now in calculating the thermodynamic properties, okay, it may be prudent to cast all these energies in terms of the temperature. So, for example, if you can easily convert it to temperature by your K, which is HC, which is about 1.4387 centimeter Kelvin the energy. Okay, the H is the Planck's constant, K is the Boltzmann constant, and this is the energy in centimeter inverse. Okay, so this gives you energy in terms of Kelvin, in terms of temperature. Okay, that is useful in calculating the thermodynamic properties. So we can define different types of temperatures. For example, translational temperature is HC by K into alpha TR. The rotational temperature is given as HC by K into BE. The vibrational temperature is given as HC by K into omega E. The electronic temperature is given by this. Okay, so the translational temperature usually will be in the range of 10 to the power of minus 16 Kelvin. So even lower translational temperatures are obtained for more massive molecules. The temperature for the rotation is about of the order of 10 Kelvin. Okay, and vibration is about 10 to the power of 3 Kelvin. Okay, and electronic is 10 to the power of 5 Kelvin. Okay, therefore, we find that both translational and rotational modes are fully operative below the room temperature. Okay, vibrational and electronic modes becomes operative when the temperature is considerably above 300 Kelvin, which is the room temperature level. So the next class, we are going to look at some of these things in a little bit more details. So there we will try to see how this translational and how these temperatures now can be used for calculating the thermodynamic properties. Thank you.